All right. In the last lecture, we stopped here where we got to the Milky Way galaxy. And the Milky Way galaxy, as I told you in the last lecture, it has a diameter of about 100,000 light years. That's huge. That means if you want to go from one end of the Milky Way galaxy and then you come back, it will take you in. If you can do that at the speed of light, it will take you 100,000 years to go and then another 100,000 years to come back. That tells you how big is our Milky Way galaxy. Now, the Milky Way galaxy, we say here it's about 100,000 light years. It may extend to 120,000 light years, depending on who you talk to. And when we talk about the number of stars that we have in the Milky Way galaxy, it may vary between 200 to 400 billion stars. So it's a huge number. One of them is the sun. And around the sun, we have planets, and that's why we call it the solar system. And the sun is not really at a very special location. It's not at the center. It's somewhere in these arms here. So that's our Milky Way galaxy. The name Milky Way, it's actually, if you're somewhere where you have clear skies and so on, away from all light pollutions and so on, and when you look through it, and that's the early observations, they saw something that resembles what looks like spilled milk. And in Latin, they call this via dilatatae. And you know what via is? Via means way, and latte is milk. So it translated as the Milky Way. And that's why the Milky Way name that it's given to our own galaxy. بالعربي نحن نسميه فيه درب التبانة. So we're not really translating literally, but we're using something to give the same meaning. So that's basically the Milky Way galaxy, which is our own galaxy. Now, what you see here, it's what we call artistic rendition of what we think our galaxy looks like. And in chapter number 5, we'll talk about the electromagnetic waves and the energies that we can collect. And scientists basically sit down and conceptualize how our galaxy would look like. So this is not a direct image of the Milky Way galaxy, but it is very close to what it should be. Now, how did we actually get to know this? There is here another galaxy that you can see here. And from this galaxy, we can get ideas. There are other different types of galaxies, which we look here and we say broad spiral galaxy, and it's given some letters and numbers, and that's the way astronomers sometimes they refer to things. So galaxies are not one thing, they are different. They have different shapes, they have different sizes, and so on. And in chapter number 10, we will basically talk about what we call the tuning fork diagram, just to show you the differences or the relation between all these different types of galaxies. And I think in our universe, in which we call the observable universe, what we can see. And by the way, when we'll talk about this in chapter number 10, we only see 4% of our universe. The other 96%, it is basically what we call dark matter and dark energy. And that's why you always hear people say the observable universe. بالعربي الكون المرئي. So we only look at about 4%. And I think the estimates now, when we talk about that, maybe about a trillion galaxies or something like this. And each galaxy depending, so in sizes and the number of stars in it. But if you look at our own galaxy, I told you it contains somewhere between 200 to 400 billion stars. Now, our own Milky Way galaxy, it has some neighbors, and this is what we call here the local group. And the local group is a cluster, and you know what a cluster is. A cluster means it's a group of galaxies, probably about 22 galaxies. One of them is the Milky Way Galaxy. So we say that our Milky Way Galaxy is within the local group, and that's basically if you are at a distance of about several million light years, just to tell you how vast is our universe. And that's basically our own cluster of galaxies. And we exist within this local group. Now, these clusters, like what we talked about, like the local group cluster, they actually group together to form something that we call super clusters. So we have a super cluster that contains a huge number of clusters. And then the superclusters form what we call filaments, okay, and walls around voids. I usually always look at this if you take a piece of cotton and you can take one strand of this cotton, and that could be like a filament. And of course, you can see voids between them. Voids معناها فراغات. And that's basically now our universe on a large scale. So the universe is made of filaments, and the filaments are made of superclusters, and the superclusters are made of clusters of galaxies, and galaxies are made of stars, dust, and gas. And in our case, we happen to be a planet orbiting a star like the sun, and life exists on this planet. And if we look at a universe that may contain 1 trillion galaxies, and one of these galaxies is the Milky Way Galaxy, and the Milky Way Galaxy contains between 200 to 400 billion stars. One of them is the sun, and around the sun we have planets, and one of them is the Earth, and life exists. So what are the chances that there are situations like our own, and life exists there, but what form of life? And that's why at the beginning of the chapter we ask, what are we? Not who are we? Now, just to give you an idea, that's what we call deep field view. And what you see here is basically a huge number of galaxies to tell you how vast this universe is. Of course, when you look at these galaxies, you may actually see different shapes and so on, and colors and so on. And we'll talk about this in chapter 9 and 10 to shed some light on this. So if we want to look at this, or if you can basically you live on a planet Earth, and this planet Earth is part of the solar system, and the solar system probably part of a galaxy, and the galaxy is part of what we call that's your solar system. There are some neighboring stellar there, then you are within a galaxy, and this galaxy basically within a local group, and the local group basically is part of a supercluster, and the supercluster is part of a filament, and the filament basically forms the strands that forms our own universe. So the universe is huge. So now, if you really want to identify yourself, you can say, well, my address is, if you take it from here, you will say, I live in Al Ain, in a country called United Arab Emirates, in a continent called Asia. It's on a planet, Earth, and Earth is a planet in the solar system, so you have to identify that. And then you say, this solar system exists in the Milky Way Galaxy. And then you can say this Milky Way Galaxy is part of the local group. And of course, we don't have names for the supercluster and the filaments and so on. And then you go to the universe. So if you want to basically state your address within the universe, that's what you have to go through. And that tells you how vast is our own universe. Is this clear so far? Any questions on this? You can use the mic. You can ask questions by chatting as well. So do we basically make these things up, or this is a knowledge that has been generated by humans? By the way, for a very long time, humans thought that the Earth is the center of the universe. They didn't even have an idea what the universe is. And then about 400 years ago, the view changed from the Earth being the center to the sun being the center. And currently, we say, no, we don't know where the center is. The sun is basically the center of our solar system. And it exists in a galaxy, and we have a huge number of galaxies, so we don't really know where the center of the universe is. But we all change, and this depends on our methods and so on. So what we do here, we follow something that we call a scientific method. And here I should bring in a point between two different subjects. There is a subject that called astrology, and there is a subject which is called astronomy. Here we are studying astronomy. Astrology is basically, it's not a science. They just look at the location of stars and they try to assign events maybe to it, which has no, they have some rules, but it's not as what we have here. So astronomy is a science. Astrology is not a science. Nowadays, in our own Islamic culture, we look at astrologers as munajjimun or munajjimin. And that's, of course, a word that it's not really accepted, so they refer to themselves as falakiyin, but they have nothing close to this. Astronomy, falak; astrology, tanjim. So you should make a difference here. But now, even those who are try to use tanjim, they try to call themselves falakiyin as well. And there is a scientific method that we follow when we try to study astronomy or science in general, we always start from an observed facts, and we call this phenomenology. So an example that I can give you, if you take a pen and you let go from a certain height, it will fall down. If you take anything and you bring it to a certain height and you let it go, it will fall down. And that was basically known as free fall. Now, if I ask anyone, will say, well, due to gravity, because the Earth basically can pull things down toward it because of a gravity. Before that, it was basically a phenomenon, which is known as free fall, because we don't see any force pulling them down, but yet they fall. So that's an example. So that's usually in science, when it's a fact, and then it becomes a phenomenology, and then what we try to do is to explain this. What is the explanation for this? And when you try to explain things, you'll try to come up with ideas. And this is where we come with a hypothesis, and it may develop into a theory. And that's how we think why this is happening. Of course, we have to test this hypothesis, or we have to test this theory. So we'll say, if this is right, the theory will predict this. So we have to have what we call testable predictions to see if the hypothesis or the theory is correct. Now, if the predictions are okay, then we look for further observation to test these predictions. Now, of course, if we have contradiction, that means the observation contradict our hypothesis or a theory, then finally either reject or we try to modify this hypothesis or theory. But we don't have to stop if we always continually have to go back and forth to test this theory, and that always happens in science, where we have more and more accurate observations and so on. We always have more and more new instruments and so on, and we try to improve. So we do fine-tuning at these. So here, an astronomy or falak, it is based on a scientific method, and that's what a scientific method is. Now, there are sometimes what they call pseudoscience or something of that sort, and people try to make some rules to how to do that. And again, I just want to make sure that you know the difference between astronomy and astrology. Nowadays, you may actually, bil Arabi, you hear people, everyone saying, I am falaki or I'm in falak, and they're basically trying to use astrology, and they're not even good at astrology, but they take it as a way of making money, especially if they appear on TV and so on. Just to make this clear. Is this clear? Any questions so far? Now, the second thing that I want to do with you here is basically we're going to deal with something that we call the powers of 10, even though I did it. But in math, if you raise anything to the power 0, you get 1. But if we say 10 raised to the power 1, that means it is a 10. If we say 10 raised to the power 2, that means it's 10 times 10, which is 100, and that means it will give you 2 zeros in front of the 1. 10 to the 3, that means 10 multiplied 3 times, which gives you 1,000, and that's why we write it here as 10 to the 3. That means it's 1 and 3 zeros in front of it. And so on, 10 to the 4, 10 to the 5, 10 to the 6, which is 1,000,000. So we write that as 10 to the 6. And a billion is 10 to the 9. A trillion is 10 to the 12. So you can see, if I want to write a million, and if I just write it as 10 raised to the power 6, that's what we call the scientific notation. It will make it easier for me to write this big number. Again, if you're looking at a trillion, for example, how big you have to write the number, but you can write it as 10 to the 12, and that basically saves you time in counting zeros and so on. So this is we call a scientific notation. And it makes it easier for us to write these big numbers. The same thing happens when we look at the small numbers. In the same way, if I want to, let's say, write, you know that in a centimeter, you have 10 millimeters. So a millimeter is 1 over 10 from a centimeter. So we write this as 10 raised to the power minus 1. That means you invert, which is 0.1. 10 raised to the power minus 2, it means 1 over 100, which is 0.01. And 10 raised to the power minus 3 is 1 over 1,000, which is 0.01. And that's a millimeter. 1 over a million, which is 10 raised to the power minus 6, is a micron. And 10 raised to the power minus 9 is 1 over a billion. And that's what we call a nanometer. This is, if you look at what we have here, you only write something like this, which makes writing a big, more digits in a very compact form, and we call this a scientific method. So that's basically make things clear. So remember when we talked about the light year, we said the light year is 10 raised to the power 13 kilometers, or 10 raised to the power 16 meters. So we use that. Now, in the next slides here, we're going to look at zooming in, okay, not zooming out. We already done this, but we can do it. So you are somewhere, I want you to concentrate on the red square, what we have in the red square. So you are 10 million light years away from the Milky Way, and then you zoom in, and you can look at the bottom here, and you have here 10 raised to the power 23 10 raised to the power 23 meters. Now, if we basically zoom in, you are somewhere on the edge of the Milky Way Galaxy. If we zoom in further, you are basically in that region, and this region we picked it because this is where the sun exists. You are in the Milky Way Galaxy, and you see dust, gas, and stars. And 100,000 light years is basically the size of our own galaxy. You zoom in or you dive, and you can see dust, gas, and stars. Further, you see nothing but dust, gas, and stars. Again, this is about 100 light years away from the Earth, nothing but stars and dust and gas. Okay. Now you come to about 10 raised to the power 16, which is 1 light year, and you can barely see the sun glowing here. If you basically come to 10 to the minus 15, which is 1 trillion kilometers, you can see the sun, at 100 billion kilometers, which is 10 raised to the power 14 meters. You can see now we put orbits. This is color. That's artistic. We cannot see this. When we talk about the solar system, that's not seen. You see planet orbiting, but we are adding in the orbits of the planet just to show you that this is something that you can see orbiting the sun. Again, you start diving in, and when you come closer, you can see the blue orbit here, and the blue orbit of the Earth around the sun. You dive more, and you can see now a white orbit around a dot here, and that's basically the moon around the sun. And I tell you again, these blue colors and white colors, they're added in just to show you the path of the Earth around the sun. That's the blue, and the white is the path of the moon around the Earth. If you dive in, now the Earth become a little bit clear. You come to 10 raised to the power 8, which is about 100,000 kilometers away. You can see the Earth. Now at 10,000 kilometers, that gives you, remember when we said the diameter of the Earth is 12,756 kilometers, so about 10,000 kilometers is very close to the diameter of the Earth. Now if you look at the square, and this is basically the southern eastern United States. You dive in more, and now you are in Florida. And at 10 kilometers, it's like the size of a city. That's the Tallahassee in Florida. It's a city. Now you come at 1 kilometer, and you can see something that could be the size of our university, or maybe smaller than the size of our university, but it's a campus, and that's called the National High Magnetic Field Laboratory, and that's basically where this program was made. It's called the Powers of 10. Now if you dive in at 100 meters, and that could be, let's say, if you in the university, it could be the size of one of our buildings like the C6 or C1 and so on. At 10 meters, you actually, that's the size of a tree from one end to the next end. Now at 1 meter, okay, you can see clearly some tree leaves. And if you go to 10 centimeters, now at 10 centimeters, you can basically see clearly leaves on the tree. And we use the tree here because it signifies life. Now, this is 10 raised to the power minus 1. And 10 raised to the power minus 1 is about 10 centimeters. So we actually went from positive to negative now powers. That means 1 over. And 10 centimeters, if you have a ruler or you look at your hand, probably your hand is about 15 centimeters. And you can basically see these tree leaves. Can we dive further? By the way, in this course, we're not going to look at small things. We're only looking at bigger things. But to give you an idea of the knowledge that we have generated as humans. Now, if you go down to about a centimeter, you can see some structure in this tree leaf at 1 millimeter. And you can use a magnifier or a microscope to look at that, and you can see some structures at 100 micron. And by the way, your hair the thickness of your hair is about 70 micron. So what you see in this image here, from hair to hair, it's like a hair. So you magnify the thickness of your hair and you see this. And now you can see some structures here and you see some cells. Okay. If we go to 10 microns, and at 10 microns you can see individual cells. And you know that every living thing can basically made of cells. At 1 micron, you are basically seeing the nucleus in the cell of the leaf. And at 10 raised to the power minus 7, you see something that we call chromosomes. And that's essential in all cells. And you all know that for humans, we have, females have X and X chromosomes, and men have X and Y chromosomes. Now, if we magnify more, at 10 raised to the power minus 8, you see something that we call individual DNA. And you know that the DNA is the blueprint which makes your hereditary line, any of these things. Okay. Now, if we magnify more, you can basically see what we call the building blocks of the DNA, and that's on the order of a nanometer. And this is basically, it's like molecules, but these molecules made of atoms, and most of these atoms, when we talk about organic things, it's made of carbon. So at 10 raised to the power minus 10, now you are face to face with a carbon atom. And you all learned in school that atoms have a nucleus, and inside the nucleus you have protons and neutrons, and around them you have electrons. So if you magnify more, you are in the cloud of the electrons. Cloud of the electrons, but now you can see the nucleus that we have inside the atom, or carbon atom, at 10 raised to the power minus 13, which we call 100 femtometers here. You can basically see some particles inside the nucleus. At 10 raised to the power minus 14, you can see the nucleus of the carbon atom, which basically contains 6 protons and 6 neutrons. Now, at 10 raised to the power minus 15, you are face to face with a single proton. And in physics now, we can break these protons. And we found out that it's made of something smaller that we call quarks. If you go even smaller, we can get to something which is smaller than that, which we go to something that Higgs bosons and many things like that. So now, in this course, we're not going to look at these things, but to give you an idea, scientists, when they look at the universe and they see the universe is expanding, so they try to go back. Okay. And when you go back, if something expanding, it will become smaller and smaller and smaller and smaller. And they say we will go to a point where the universe originated from, and they talk about something that we call the Big Bang. And at the time of the Big Bang, you did not have matter. You only had energy. And from that energy, quarks and electrons came, and the quarks, they come together to form protons, and the protons and electrons, they form a neutron. But the hydrogen atom, if you look at a hydrogen atom, the hydrogen atom has one proton in its nucleus, and one electron orbits the hydrogen atom. So they say the first element that came into existence, basically forming from energy to matter now, it's hydrogen. And then gravity kicked in and it started collecting this hydrogen to form stars. And when the gravity is contracting the hydrogen to form a star, well, when things are basically contracting, they're under high pressure. And if they're under high pressure, the temperature rises up. And then there is enough force that can fuse two hydrogen atoms together. That means it brings them in. And that's exactly how the sun is basically producing energy. And we'll talk about that in chapter number 8. So it takes 4 hydrogen atoms to form helium. And it continues like that to go to higher elements. Then the star becomes big and it explodes. And when it explodes, it's make a nebula. And in this nebula now, you have lots of elements. Again, a new star begins, and that's when we talk about how our solar system came into existence. A new star basically come into existence, and around it you have a thin disk of material, and this material basically starts over a very long period of time. It collects to give you what we know as planets, and that's how the solar system came into existence. And if we we'll talk about time scale here. So if we basically try to address this in terms of time scales, I will write on top of this slide here. The universe is basically approximated to be 13.8 billion years. That's how old is our universe. That means the initial point of the Big Bang. Now, our solar system is 4.6 billion years. So it took a very long time before our solar system came into existence. And now, so the Earth is about 4.6 billion years. Your age as humans, it's only 200,000 years. The Earth is about 4.6 billion years. You're only 200,000 years. That's the age of humans. And of course, you know that there are dinosaurs before us and so on. So that's how we fit things on this time scale. Okay. So you live in a universe that is 13.8 billion years. Yeah, you should know these numbers. Okay. The age of the universe is 13.8 billion years. The age of our solar system now is approximated as 4.6 billion years, which is basically the age of our Earth. And there are many arguments on this and how old are humans. Before us, there are life started, and then we have dinosaurs, and the dinosaurs now, they no longer around. And we can talk probably about this. And then when it comes to humans, there are lots of debate. When did basically human arise on the surface of the Earth and how they moved and so on? That's a big debate. But to good estimates, they always say probably humans started about 200,000 years ago. So you're relatively young to this universe, and the universe is vast, and that's why now there are many who are basically asking questions if there is another form of life out there. Now, since the early 90s, astronomers start discovering what we call extrasolar planets, which known as exoplanets. These are planets that orbit other stars, not our star, the sun. And now the number, I think it's near 4,500 exoplanets have been observed. That doesn't mean the number is much bigger than this, but our techniques in trying to observe them, and we'll talk about this in chapter number 6. So there are other planets orbiting stars, not our own sun, and there always the question is, will there be conditions like our own where will be life, and what form of life will it be, and is it intelligent form of life? And that's why the question at the beginning when we said, what are we? It's not who are you. So that's the beginning, and the time scale, as I told you, age of the universe is about 13.8 billion years. Age of our solar system is 4.6 billion years. Humans around 200,000 years. But actually, when they try to look at DNA and things like that, and fossils and things like that, I think now they're going back to about 65,000 years when they think a human is erected and can walk and things like that. Okay. Now you can ask questions if you have any, okay, and you can use the mic as well. But now there are or common misconceptions here. Light year is a unit of time. People always hear the word year, and they think it is time, but light year is a measure of distance, not time. Stars look like disks when you see them through a telescope. When you look at the sun, it looks like a disk to you, but the sun is a big sphere. Okay. But it only looks like a disk because it's further away from here. And people often say galaxy when they mean solar system, and they sometimes confuse both terms with universe. So it should be clear into your mind that we live in a universe, and this universe is 13.8 billion years old. It contains a huge number of galaxies. One of these galaxies is the Milky Way Galaxy, which is its own galaxy, and this galaxy contains between 200 to 400 billion stars. One of these stars is the sun, and around the sun you have a planets, and one of these planets is the Earth, and we happen to live on the Earth. I think with this, I just want to give you an overview of where we are located, and we will proceed from here. Is this clear? Any questions on these? Good. So the next thing that I'm going to do here is I'm going to look at something that I'm going to call review questions. And these review questions, it's a question and possible answers, and you have to look. And in here, basically the answers are given in red. So the first question here, A solar system contains primarily planets, large amount of gas, dust, but very few stars, large amount of gas, dust, and stars, a single star and a planet, thousands of superclusters. So the solar system, the only logical answer here is a single star and planets. Of course, it will also contain moons and it contain asteroids and comets and many, but they're not mentioned here. But if you look at C, large amount of gas, dust, and stars, you're talking about galaxy. You're not talking about a solar system. The second one here, a galaxy contains a large amount of gas, dust, and stars. How many centimeters are there in 1 kilometer? You know, 1 kilometer contains 1,000 meters, and each meter contains 100 centimeters. So the answer here is 100,000 centimeters. Scientific notation, remember when we talked about the powers of 10, it makes it easy to write large or small numbers. That's the scientific notation. The average distance from the Earth to the Sun is 1 AU, which is equivalent to 150 million kilometers. Now, this one here requires a little bit of logic. We're not going to deal with math here, but we're going to do a little bit of arithmetics. If light takes 8 minutes to reach Earth from the Sun and 5.3 hours to reach to Pluto, what is the approximate distance from the Sun to Pluto? You know that the distance between the Earth and the Sun is 1 AU, and 1 AU light basically takes 8 minutes. So what is the distance between the Sun and Pluto if light takes 5.3 hours, but I have to convert that into minutes, so I multiply it by 60 minutes. Now we do cross multiplication here, so the x will equal to 1 AU times 5.3 times 60 minutes divided by 8 minutes, and it will give you 39 point something, which is roughly 40 AU away. 7, the Sun is a star, and right away you think that this is the right answer. Well, you have to look at all the answers first. Second, 1 AU from the Earth. C, more than 100 times the diameter of the Earth. And yes, the Sun roughly is about 109 times the diameter of the Sun is 109 times the diameter of the Earth. So that's also true. So actually the answer here, I made a mistake, okay? The right answer here should be all of the above. That's the right answer. Okay. This is E is the wrong. It's a typo here. But the right answer should be all of the above. And you really have to look at this question carefully when we do this. Now, if the nearest star is 4.2 light years away, which we talked about this one, said Proxima Centauri, the light we see left the star 4.2 years ago. That means when we look at the star, we're not seeing the star right now, we're actually seeing the star 4.2 years ago. The Milky Way Galaxy is about 100,000 light years in diameter. I told you that in some other writings you may find it as 120 because they look at thinner extensions and so on, but roughly speaking now it's accepted to be 100,000 light years in diameter. Which of the following is the largest? The diameter of the Earth, diameter of the Moon, diameter of the Sun, diameter of Jupiter, or the distance between the Earth and the Sun? Of course, it's the distance between the Earth and the Sun. We know that the Sun is the biggest object in our solar system. Then Jupiter is the biggest planet. It's bigger than the Earth, and the Earth is bigger than the Moon. But actually, the distance between the Earth and the Sun is bigger than all of these. Which arrangement is an order of increasing size left to right? So the right order is planet, star, solar system, and galaxy. The Milky Way Galaxy contains more than 100 billion stars because there is argument on the number of how many stars we have. That means how far you want to go from the center of the galaxy and so on. Now, there is an argument between 200 to 400. Before that, it was less, but so we'll just say more than 100 billion stars. In science fiction movies, it is common to use a spacecraft to travel across the Milky Way Galaxy or to assert that we have been visited by alien spacecraft from the other side of the Milky Way Galaxy. If one has a spacecraft that can travel at the speed of light to an observer on the Earth, how long will it take to go from one edge of the Milky Way Galaxy to the other and return? And we already discussed that in the lecture. So if the diameter is 100,000 years, and you can do that at the speed of light, then it will take you 100,000 years to go, and then 100,000 years to come back. So the answer here is 200,000 years. This question here relates to the models that you see when we talked about, when we try to have a scheme of the solar system. Earth has a radius of about 6,400 kilometers. Remember when we said that the diameter of the Earth is 12,756 kilometers. Roughly speaking, 12,800 kilometers. Radius is half of the diameter. So half of that will be 6,400 kilometers. Now I told you that the Sun, the diameter of the Sun is 109 times the diameter of the Earth. And we say here that the Sun has a radius of about 7 times 10 to the 5 kilometer. We're talking about the radius, not the diameter, and the radius is half of that. And a rubber ball has a radius of 6.4 centimeters. If you were to construct a scale model of the solar system using the rubber ball to represent the Earth, what is the radius of a ball needed to represent the Sun in your model? So you're using a ball that you can fit in your hand. So the diameter of the ball will be about 12.8 centimeters. So this is how high the ball is. You always look at the diameter of it. Now I want to use another ball to represent the Sun. So what should be the diameter of this? Now if I say I use 6.4 centimeters to represent 6,400 kilometers, so what is the radius needed to represent 7 times 10 to the 7 times 10 to the 5 kilometers? So the R here will equal to 6.4 times 7 times 10 to the 5 divided by 6,400, and it gives me 700 centimeters, which basically 7 meters. That's the radius. That means if you put the ball from the ground all the way up, the ball will be 14 meters high. That's like a 3-story building. That's about 3 high-story buildings. And the ball will be something that you fit in your hand. That's if we want to make the model to scale. So when you go to the market and you buy a model of the solar system, it is not done to scale. It is representative. Okay. But if you really want to do it to scale, then the Sun either have to be very big, or you're not going to see the planets anymore. So what you buy in the market is basically not to scale. It's just basically to represent things to you. Which sequence is correct when ordered by increasing size? Earth, solar system, Milky Way, and galaxy clusters. Others will basically are not going to fit this. How is a planet different than from star? Planets reflect light while stars produce their own. So that's the main difference. The sun is a star, produces light. But when you look at other planets, they actually only reflect light, and that's how we see them. 17, if we say that an object is 1,000 light years away, we see it as it looked 1,000 years ago. And that's why I told you, when you look at the night sky and you look at the stars, you are not seeing them now. You are seeing them in the past. We have no idea if the star is still alive or dead now. But we just still have to wait to receive the light that left the star. Finally, here we have true, false, but of course this is not something that I'm going to give you in your quizzes because it only gives you 2 options, but I'd like to give you 4 options. So in your quizzes and midterm and a final, you will be given multiple choice questions and you really have to choose the correct option. The idea of these review questions here is to understand these questions, not to memorize them. I can take one of them and reword it in such a way that it may look different, but if you understand, you will basically answer that. Now, some of you, they ask what numbers they should memorize. Well, the type of questions that I'm going to ask you, I'm not going to ask you to state the number. But what I'll ask you is to recognize the number. So if let's say if I ask a question about the speed of light, and I will say the speed of light is, and I give you 300,000 kilometers per second or 100 and so on, you have to recognize the number. So I'm not going to ask you to memorize the number, but what I will ask you is to recognize these numbers. So the idea here is understanding, okay? But it is advisable, especially you live in this time, you should know what the speed of light is. You should know how big is our Milky Way galaxy, how far is the sun from here. These things, I mean, is knowledge which you should know in this time. True, false, the average distance from the sun to the from the earth to the sun is 1 AU. That's true. The nearest star is 1 light year away from the solar system. That's false because the nearest star is Proxima Centauri, which is 4.2 light years away. A light year is the distance traveled travels in 1 year. That's true. A kilometer contains 1 million meters. It contains 1,000 meters. That's just logic. So that's false. The metric system is a decimal system. So many of you probably, your height, if it's 170 centimeters, we write it as 1.7 meters. And that's what we mean by a decimal system. The sun is a star in the Milky Way galaxy. That's true. The local group contains the sun and only about 2 dozens of stars. The local group is a cluster of galaxies, and one of these galaxies is the Milky Way galaxy. That's why it's false. A supercluster refers to a large group of stars within the Milky Way. That's false. A supercluster is a cluster of clusters of galaxies. A kilometer is a larger measure of distance than a mile. The mile is greater than a kilometer. Mars is further from the sun than the Earth, and that's true. So the idea of the review questions here is that when you study, you have to understand why this is the right answer. It's like testing you, okay, and how to deal with this. So, and if I want to summarize all of this, I can say that we live in a universe, and this universe is about 13.8 billion years old, and this universe contains probably trillion galaxies. One of these galaxies is the Milky Way Galaxy, and this Milky Way Galaxy has a diameter of about 100,000 light years, and it has a number of stars that vary between 200 to 400 billion stars. One of these stars is the Sun, and around the Sun we have planets, and the third planet from the Sun, sometimes people refer to it as the third rock from the Sun. And Earth happens to have an atmosphere that have liquid water, and liquid water is essential for life. This Earth is about 4.6 billion years old, and we humans became basically late. So our age is about 200,000 years. So if you compare 13.8 billion years, which is the age of the universe, to 200,000 years, as if you came in the last second, compared to all of this. And with this, we can chapter number 1. So all the chapters that we deal with, we always have review questions at the end, and these review questions, you can look at them. They actually help you understand the material. Do you have any questions? Any questions? Is it clear? All right. Good.